have your course at a glance, this guy, I'm gonna start putting the learning objectives right off the bat. They were too long, so I just put LO. Whenever you see LO, it means learning objectives. And if you're following along and you have your binders or you have your course at a glance, I put in here that we are covering 1.3. 1.3 is estimating limit values from graphs, which we kind of already did yesterday, but we're going to do a little more advanced ones today, composite functions and all that good stuff. And then I put 1.5, determining limits using algebraic properties of limits. That's what this is, properties of limits. And then I put 1.10, exploring types of discontinuity. So we're going to talk about all those. And then there's some more that are embedded, but they don't make a big splash just yet. So if you're following along, you can highlight them. That's what we're covering today. And if you go to the very last page, it's going to say activity 2. And what I decided that we're just going to do activity 2 tomorrow in lab, because I don't want to hit you guys too hard just yet. So activity 2, we'll worry about that one tomorrow in lab. And then we just have one quick delta math. So after today, hopefully you'll be pretty ready for handout activity. And then the handout activity we'll cover tomorrow in lab. So, and then make sure that your UH accounts are active, because that's coming up pretty soon. All right, how are we feeling, guys? Are we feeling okay? All right, so here are the properties. They're not all that extreme, guys. It says if L, M, C, and K are real numbers, and so they're telling you that I have some limit as x approaches C, it's equals to some number value L, and I have some limit as x approaches C for G of x, and it approaches some number M. This is F, and this is G. That you can add them up, limit as x approaches C, as long as they're approaching the same thing, f of x plus g of x. That's not a hard property to know. Plus minus is still the same thing. Product, same thing. Sometimes I like to rewrite this one. See how that says k times L? So you can rewrite, if you have k times f of x, you can rewrite this as k limit as x approaches C of f of x. So sometimes I take advantage of that property, and there it is. And the quotient rule, as long as m is not 0. So see, they're pretty basic. And then the power rule. So don't worry, we're going to talk about all these rules. What's up?
No, I was just going to ask you to explain number 4.
Yeah. I can explain it differently. So let's say I have something like, let's make a simple function. Let's say I have a f of x equals, let's make a simple one, like 5. So we know that this function looks like this, right? It just goes at 5 forever. So if I have something like limit as x approaches 3, we know that if I approach any number, it doesn't matter what I approach. If I call this f of x, it's always going to be 5. But if I have 3 times f of x, that just means I can rewrite it as 3, limit as x approaches 3 of f of x. And what is 3 times 5? And check it out. If I would have just done, well, what is 3 f of x? Well, this function is always 5. 3 times f of x is now just going to be 15 always. So if I were to graph 15, here's 15. It doesn't matter where you go, it's always going to be 15. Does that make sense? That's the easiest example I can come up with right off the top of my head. There's other examples. We could have done like a unit 1 or something, a step unit, but I just wanted to keep it simple. Is that enough to comprehend that property or no? Okay. Yeah. Hit me guys with questions. I'm always down. Math life all the time, 24/7, 365 days a year. Okay, I'll stop. All right. It's the same properties, guys, so look what they're telling me. Limit as x approaches 4 for f of x is 0. Limit as x approaches 4 for g of x is 3. I'm approaching the same x value. I have two different functions, an f and a g. Nothing crazy. So using the properties, limit as x approaches 4 for g of x plus 3. Well, let's see. According to this right here, look, f of x plus g of x. It doesn't matter. F of x can be a constant. All I'm doing is adding them up. So let's see. I can go, what is 3 plus 3? And that's it. Don't worry, we'll go slow. Letter B. Limit as x approaches 4 of x, f of x. That x is a 4. I'm going to do direct substitution, if you can. And I know we haven't talked about direct substitution, but don't worry, we'll figure that out right now. And if I approach 4 for f of x, that's going to be 0. What's 4 times 0? 0. So this limit is 0. Notice that I started plugging in numbers. So once you plug in numbers, you don't have to write the word limit. Limit as x approaches 4 for g of x, but notice that it's quantity squared. Let me rewrite this differently in case maybe this helps. It means this. Well, limit as x approaches 4 for g of x is 3. And what's 3 squared? Yeah, that's it. limit as x approaches 4, as long as I'm approaching 4, g of x is 3, f of x is 0, so 0 minus 1, so that's negative 1. 3 divided by negative 1? Negative 3. I'm just doing direct substitution when applicable. As long as you don't get a 0 in the denominator, guys. Yeah, this one says x times f of x. I can rewrite it. Limit as x approaches 4. This will become easier to understand once we start talking about the general rules of limits. So I have some function and I'm multiplying it by x. Well, what is x approaching? So I'm just going to go 4 times. But f of x as x approaches 4 is 0. So it's just like 4 times 0. Let me know. I could always explain it differently. We're just using the properties. That's all we're doing, guys, if applicable. Let's see. They tell me that if I approach C, it's 3 for F, it's 5 for G, and it's 2 for H. And I should be saying it correctly. Limit as x approaches C for the function f of x equals 3. Limit as x approaches C for the function g of x equals 5. Limit as x approaches C for the function h of x equals 2. So you guys practice saying it. Let's practice saying 1. Repeat after me. Limit as x approaches C for f of x equals 3. Perfect. You said it perfectly. That's exactly how you say limit. All right, here we go. This is approaching C. They're all approaching C, all these limits, because they want to use the properties. So what is the limit as x approaches 3 for f of x? 3. So I'm going to write 3 plus, and this is just 5 times g of x, so I'm going to write 5. What's the limit as x approaches C for g of x? 5, and there it is. What is, let's see, what's 5 times 5? Plus 3. There it is. That equals 28. That's all you're doing, guys. Limit as x approaches as x approaches C for g of x, and I'm cubing it. So if I approach C for g of x, that is 5. And do we know what 5 to the third power is? 5 times 5 is 25, and if you have 5 quarters, that's 125. Because 25. Yeah, that's right. Now I was freaking out already. 25 times 25 times 25. So we're good. All right, here we go. Limit as x approaches C for the square root of f of x. Well, limit as x approaches C for f of x is 3. So this must be the square root of 3. And I know what you're thinking. So check it out, Ms. Rowe. Check it out. I'm going to do an example just in case. I know you didn't ask, but I wanted to do this. So let's say that my f of x was always 3. I'm just making this up, guys. I'm just making this up. Let's say that my f of x was always 3. Well, now notice, if I take the square root of that, my limit's always going to be square root of 3. Do you guys see that? So yeah, so there it is. Now, notice, is it possible for this to be undefined? Yeah. If I would have been below the x-axis, can I take a square root of a negative number? No. Well, at least not in real analysis. In complex analysis, you will, but I'll let the professor talk to you about that and holomorphic functions and all that good stuff. It's so much fun, but so much confusion. You're gonna have headaches, but good headaches, not bad headaches. Okay. Don't worry. This class is just Cal 1. It's not a big deal. It's just baby stuff. No worry. Like it's not anything extreme. I already took attendance. This is Chavez. Perfect. Thank you. We're just checking that it works. All right, here we go. Limit as x approaches C for g of x times h of x divided by, we do have a product rule. So in case you're wondering, see, all you're doing is multiplying them. And then we do have a quotient rule. So you just multiply and divide. And yeah, it really, I know some of it kind of seems like very basic, but yeah, it really is that simple, guys. Let's see, so this is going to be 5 times, what's the other one? 2 divided by 3. So 10 over 3. Done. Example 3 is kind of like a review of what we did yesterday. Relax. It's not extreme. This says, use the graph of the function shown to the left in order to determine, what does that little plus symbol mean again? From the right. You're approaching 6 from the right. So if I approach 6 from the right, so I'm looking at this curve. If I approach 6 from the right, what is that y value that you're approaching? So there it is. That's it. Limit as x approaches 6 from the right of this function equals 3. And it's okay that you have a hole. We'll talk about that today. And yeah, that's about as far as it goes. And it looks like a lot of notes, guys, but it's not. It's just that graphs take up a lot of space. So that's why it looks like a lot, but it's not a lot. It's just that graphs. Graphs take up a lot. All right, so let's go to the next example. Let's see what it says. The function f is shown to the right. Determine the equations of all vertical and horizontal asymptotes of f and the equivalent limit equations. Okay, so that means they're talking about behaviors. So first, can you identify the vertical and horizontal asymptotes? Yep, there's one. The vertical asymptotes are the easiest ones to see because it's where we go up forever. There's 2. So what are my vertical asymptotes so far? X equals -1 and x equals 6. Yay or nay? Horizontal asymptotes. I see another one. Well, okay. This is my first one. There's my first one. That one is y equals 4. And I see another one right here. Horizontal asymptotes are end behavior. Y equals -1. Horizontal asymptotes, guys. What you approach as x approaches infinity and negative infinity. Are we okay so far? Nothing crazy, right? All right, so how do I do my horizontal asymptotes? Horizontal asymptotes are end behaviors. If you have an end behavior that's a constant, that's a horizontal asymptote, and you can say this: limit as x approaches infinity. For this function, we called it f, so I'm going to call it f of x, equals, so if I approach infinity, what am I approaching? What y value? Yeah, be courageous. It's safe space. What y value, guys? Not 0. Yeah. As x approaches infinity, what does my y value converge to? I heard someone say it, but very lightly. 4. Good job. Good job, Kendra with an N. 2 N's. No, I knew it was 2 N's. YouTube, I knew it was 2 N's. I'm recording right now. So, see, so in case you're wondering, you're like, what's going on? I have no idea what you just did, Chav. Okay, look, x is approaching infinity. As you go forever to the right, what y value are you converging to? 4. See? Limit, that's not the only one. We have another horizontal asymptote. So limit as x approaches what? Negative infinity. For this function, it's going to approach what value? -1. If your end behavior is a constant, that's how you find your horizontal asymptotes. That's how you find your limit expressions. Does that make sense? Don't worry, we're going to cover it in more detail. All right, let me change the color for my vertical asymptotes. Vertical asymptotes. So I noticed that I have a behavior at -1. If you saw the videos, you're going to write limit as x approaches -1 of this function. And you can either say both from the left and the right approach positive infinity. So you can either say positive infinity or you can say it does not exist. And really, I shouldn't even be writing equals infinity because that's not possible. But for the high school, for now, that's fine. I've seen Delta do it this way. I've seen textbooks do it this way. That's fine. But I probably shouldn't be putting the equal signs there. Let's see, what else? Limit as x approaches 6 from the left and the right for this function, because the behavior is both positive infinity. You can either say infinity or what? Or does not exist. Say it again. Oh, because infinity is a behavior. It's not a number. You just keep growing and growing and growing. It keeps going up and up and up. Because you're not converging to a number, you say it does not exist because you're never going to go to a specific value. Does that make sense? Good question. Good question. I'm loving it. That sounds like McDonald's, right? I'm loving it. Okay. Do they still have that saying? Okay. So from now on, guys, vertical asymptotes, if you approach that specific value and you get a does not exist, if you get a does not exist, it's possible that you just have a jump. But if you get a behavior like positive infinity or negative infinity, it's 100% a vertical asymptote. 100%. So if you see a problem that says limit as x approaches 3 equals or is positive infinity, in your brain you should be thinking already like, oh, I have a vertical asymptote. I have a vertical asymptote for sure. And they both go approach positive infinity from left and the right. That's only if you approach a specific value. X equals c is little letters are numbers, are constants. Cool or not? Cool. Okay. All right, guys. Now we have our first composite function, relax. And I have the graph of f over here, so put f if you can't see it, and the graph of g over here. Put g if you can't see it. I'm going to go really, really slow. I'm going to go real slow. They want to know what the limit is as x approaches negative 1 of f of g of x. Chop, how do I do this? I've never done this before. It's just like your composite functions. First, I'm going to write the word first. Evaluate limit as x approaches negative 1 for g of x, if it has a limit. All right, if I approach negative 1 for g of x, what does the y value look like to you guys? 0. So now that I got 0, now I'm going to go second, I'm going to put second, evaluate limit as x approaches 0. Notice that I put 0, I didn't put a minus or a plus, so that means from both sides, of what function? F of x. So let's see, if I approach 0 from the left, it's 7. If I approach 0 from the right, it's 3. Do I approach the same number? So this one does not exist. And if you're talking to a professor, he or she's probably not going to like the equal sign. It's not a big deal. Limit as x approaches 0 of f of x does not exist. You should probably delete the equal sign, but I have bad habits, so there it is. They wouldn't count it against you, you're fine. Cool or not cool? Okay. I probably should have switched. You know what? I'm going to switch this example next time because we're not ready. Well, you guys are ready. You guys are not confused, but I should have made it like where it does exist. So for next year's notes will be even better. Switch example. And I thought I caught it last year because all these notes have been revamped, by the way. It took a lot of time for me to revamp them. So I hope you guys like them. You know, I shouldn't have touched. You see, that year, 2023, we had 100% qualifying. I should have left my notes untouched. I don't know why I touched them. But anyways, you gotta adjust them. You gotta adjust them, right? You can't leave them the same. All right, here we go. Again, same thing, but this time, and I know, sorry, what is it called? OCD or something? I changed the graph. This one's now G and this one's now F. And I know when I was doing this with the high school teachers during the summer APSI, there was one participant that was like, "You had FG on this one, you have GF on this one, please put it like in." And I'm like, "Okay, sorry, I'm just all over the place all the time." That's just me. That's how I've always been, guys. I apologize. If we have anyone that bothers them and that irks them, let me know and I'll try to be perfect. All right, here we go. So what am I going to do? They want limit as x approaches 4 for f of g of x. Which one do I do first? G. So limit as x approaches 4 for g of x. So I look at my g graph. This time it's on the left. As I approach 4, what is the y value for g? 0. So now what do I do next? Limit as x approaches 0 for which function? F of x. Perfect. So now if I approach 0 from the left and the right, what is that y value? 2. There it is. There it is. Both of these go down here. I just didn't have enough space. Yay or nay? Perfect. Let's go to the next example, guys. So this time we have a little product. So this time we can just write it like this. Limit as x approaches negative 1. And I have a product, f of x times g of x. And that's not a big deal. I'm just going to find the limits for both and then just multiply them. If I approach negative 1 for f of x, here's negative 1. What is that limit? It's that whole. What is that limit? Negative 5. See, it's this value right there, what you're approaching. Not negative 4, but negative 5. And then for the other one, a negative 1, it looks like it is negative what? Negative 4. What's negative times a negative? Positive. So it's a positive 20. And that's it. Are we getting it, guys? All right, so 2 years ago when I taught it to the class, this is the same question from 2 years. When I taught it to the class of 23, I thought it was easier to just talk about what is this compared to this, and it just means horizontal shift 3 to the right. That's what I thought it was easier. But the class of 24 thought it was easier to just do direct substitution. Negative 2 minus 3 is negative 5. And I can see that in negative 5 I have a vertical asymptote. So I can already see it doesn't exist. So class of 24 thought that was easier. Class of 23 thought it was easier to just move this graph 3 to the right and then look at negative 2. Whatever you think is easier, guys. So let's write it. Limit as x approaches negative 2 of f of x minus 3. equals, if I plug a negative 2 in there, negative 2 minus 3 is negative 5. And notice that at negative 5, you have a what? Vertical asymptote. So does my limit exist? Limit does not exist. You can also think of this function as moving 3 to the right. And if you move it 3 to the right, you have a vertical asymptote of negative 2. Whatever you think is easier. Are we okay so far, guys? All right. This is just like what we did yesterday. So I think I think it was yesterday. So it says, use the graph of the function shown below in order to determine all values a for which limit as x approaches a is negative 2. So I'd like to go to negative 2 and just do that. So I can see that limit as x approaches negative 6 of this function f is negative 2. And I can see again limit as x approaches negative 1 of this function f of x is also negative 2. And I can see that limit as x approaches 2 of this function f of x is also negative 2. And I have one more. Limit as x approaches 7 of this function f of x is also negative 2. That one has a lot. 1, 2, 3, 4. Yep. And all of them are solid. A equals negative 6, comma, negative 1, comma, 2, comma, 7. And that's it, guys. But you guys already did that, so you guys already have that experience. So yeah. Am I going too fast? I did chug a cold brew 30 ounce. I didn't chug it, but I finished it. Okay. All right. I'm going to keep going. And finally, we reached a definition of continuity. What did they tell you when you were in 8th grade about continuity? Or maybe it was your sophomore year. That if you can draw a graph without lifting your pencil, that it was continuous? It's the same. It's the same, guys. Let's see what it says. A function f of x continues at an interior point C of its domain. Okay. And then, okay, when you guys read these definitions from the textbook, do you guys read it and be like, I get it? No? Okay. This is what it means. I'll give you the first one here. It means this. So that if I have a graph and I'm going to do this. Let's see, endpoint of function containing left and okay. So this is A, and then the right point is B. Yep, this is B, and I'm going to call in the middle C. Why is it out of order? Guys, I don't know. That's just the way the author wrote it. And if I have a solid point there, well, I didn't have to emphasize it, but that's when you see a solid point like that, you're emphasizing it. So what they're saying here is limit as x approaches C from the left of this function equals limit as x approaches C from the right of this function. And all that, if the left equals the right, then that means that you can just write limit as x approaches C of this function. And if all that matches and all that just equals f of C, then it's continuous. And don't worry, I'm going to explain it. Come over here. So this is the main point, the f of C. If you take that out, I could have had, oh, wow, it wasn't working earlier, now it is. Okay, sorry guys. If I take this out, if I take this f of C out, this is just the definition of a limit. So I could have had an open circle and it would have still equaled whatever that value is. But now notice that I wrote f of C. Notice that I wrote f of C there. So what does that mean? That means if I plug in the x value and I get that output and I get that specific y value, then I'm continuous. Sorry guys, I didn't know PG-13. All right. So if the left side equals the right side, guys, stop. If the left side equals the right side, now I don't even know what to say. What is YouTube gonna think? You don't know. I can't see. Gonna love this. All right. All right, I'll stop, guys. So here we go. If your limit equals your function evaluated at that moment, then that is the definition of continuity, because your limit equals your function evaluated at C. Does that make sense? Like if my limit was 5, and I put f of C equals 5, well then there it is. That you're continuous. You're defined. So now you're converging at that value, and you're defined. And that's how you prove continuity. There was one free response question a few years ago that they wanted you to prove that it was continuous, and you had to do that. It probably caught my kids off guard because I had not been showing that until that time. So I'm like, dang it. So we probably lost a point or two on that, but that's fine. They still qualify. So cool or not cool? Does that kind of make sense? Don't worry, it's gonna make more sense once we do it. And then all it's saying about the other one, guys, all it's saying is at endpoints, you're continuous if you approach from the right hand side and it equals. So it's saying this: limit as x approaches a from the right side of f of x. If it just equals f of a, you're continuous. Check mark. And then for the right side, if you approach b from the left side, so it's saying limit as x approaches b from the left side of f of x. If it just equals f of b, you're continuous. That's all it's saying. Cool or not cool? And don't worry, we're going to do problems. We will do problems. All right. There are 4 forms of discontinuity. If you've seen the videos that we assigned, you probably already know all 4 of them. If you haven't, no big deal. We're going to tell you right now. This one is one that rarely comes out. As a matter of fact, I don't remember ever seeing it. It's discontinuous. It's discontinuous by oscillation. So I'm going to write that. Discontinuous by oscillation. Chop, what does that even mean, discontinuous by oscillation? It just means that it's going up and down, up and down, up and down so fast that you're not continuous at 0, because at 0 it's just there's no way you can be continuous. So I know that you can't tell here, but it's just going, that's all it's doing. As you get closer and closer to 0, it's just going up and down, up and down, up and down, super fast. Does that make sense, guys? So that's why you can't tell, like, man, is it continuous at 0? I don't know. Well, you can't tell. It's bouncing, it's literally going up and down so fast. So that's why this one doesn't come out, because it's not really that useful for everyday life, for these filters and all that good stuff. All right, which ones are the useful ones? You can be discontinuous by something called a step function. So let me write this down. So if you have something like this, this is also called a jump. In math, this is called a jump discontinuity. Jump discontinuity. It's also sometimes, the way I wrote it there, sometimes it's also called a step. So for those of you that are going into engineering and you see something called the step function, bam, that's what it's talking about. Do you see how that's a jump or how that's a step? It doesn't have to look like that. This could also be classified as a jump. If I have something like this, let's see. I'm going to do, and then I'm going to, that's also a jump. See? Jump. So jump discontinuity. What other discontinuity is there? Well, there's also an infinite discontinuity. So if I go something like, this is an infinite discontinuity. That means that you're discontinuous because you have a vertical asymptote. Infinite discontinuity. There we go. Infinite discontinuity. Cool or not cool? And then the last one, this is the one that's most applicable. What do you think I'm going to draw? What have you not seen yet? Look at this. What is that called? A hole. Holes are the only ones that are removable discontinuities. Removable. The others are non-removable. Chop, what does that even mean? Removable discontinuity, non-removable. All that means, and I'm going to slow down because I can see you guys writing like crazy. All that means is that these are the only graphs that you can make continuous by doing like a piecewise function or something. Chop, how do you make it continuous? You just fill in that pixel. A hole is just a singularity, right? A singularity that's blank, an empty pixel. So you can make it continuous by filling it in. That's the only one. So that, and what is that name called? What is the hole called? Yeah, in math, the hole, not like, yeah. It's removable discontinuity. Stop. Dang, guys. PG-13 here. Removable discontinuity, guys. Cool? Cool. You guys are funny. All right. All discontinuities can be classified as removable and non-removable. I didn't even remember if I had typed that in or not, but I guess here it is. Removable discontinuities occur when the function has a limit, holes in the graph. Non-removable discontinuities occur when the limit of the function does not exist, jumps, and vertical asymptotes. And, okay, that's enough. All right, this graph I literally stole from yesterday's notes. Everything is by design. Or from 2 days ago, I literally copied the same graph and let me put a graph that they're similar with to ease anxiety. So, see, it works. You guys don't feel anxiety, at least I hope not. So there it is. No, stop. All right, it says, find where the graph is discontinuous, identify the type of discontinuity. So where am I discontinuous? I'm going to write discontinuous. at x equals, what are my I have two values. What are my two values where you're discontinuous at? 1 and where else? 2. That's it. X equals 1. What type of discontinuity is it? It's a jump. Jump discontinuity. Discontinuity. Okay, as soon as I see someone in the hallway, I will send someone down. I promise. Okay. As soon as you see someone walking in the hallway, let me know so I can give them a paper roster. Okay. No, I'm being serious. So someone, like, just when you see someone in passing, tell them, hey, come over. And so they can grab this. Okay. It's a jump discontinuity. It's non-removable. Non-removable. All right, what about at x equals 2? That's it's removable. It's a what? It's called a hole, and that is removable. Removable discontinuity. And that's it. That's all they wanted. And that's what you're going to do today later on in your delta. So here's an example of the delta. We stole this example from delta. Find where the graph is discontinuous. Identify the type of discontinuity. So where are my discontinuities? You read a graph left to right. Discontinuous at x equals, well, there's another one before you hit 1. -4, comma, where's the next one? 1, comma, where's the next one? There's one more. Perfect. Now we're going to identify the type. At x equals -4, what type? Oh, Miss. No, yeah, for reals. Come in real quick. Can you send something to the office? I owe you a taco, miss.
Give me a purple pass, they're gonna yell at me.
Okay. Here.
Thank you.
Mm-hmm. Okay. X equals -4. That is a hole. And a hole is what type of discontinuity? Removable. All right. And then what about at 1? It's a jump. And what type of discontinuity is that? Non-removable. Non-removable. Sorry that my handwriting is messy. What's the next one? 6. And what type of discontinuity is that? It's a hole, and that is removable. All right, that's it. Let's see. What else do we got? Again, same type of deal. Same type of deal. Let's see. Read a graph left to right. What's the first one? -6. What's the next one? -3. What's the next one? 4. All right. At -6, what type of discontinuity is that? Hole, and that is removable. What about a -3, guys? What did that one call? Start with letter I. Infinite. Infinite discontinuity. And that is non-removable. And I got another one. Where's the last one at? And what is that? Another infinite. And I think, did we cover everything? All right, check it out, guys. These questions here are legit, real AP questions. So see, right off the bat, second day of school, you're seeing real AP questions. From what exam was this one from? 2012, the international exam. So take a minute, see if you guys can figure this out, and I'll give you the answer in a little bit. So take a minute, see if you guys can figure it out. No, you would have gotten it right because we're about to hit you with a testing strategy. All right, they want a false one. They want a false one. Let's say you're in a hurry and you're taking this test and you read it and you circle the letter A because you're like, oh, that one's true. It's true. Guys, look at the other answer choices. So look, let me give you a testing strategy. So it says, the graph of the function f is shown to the right. Which of the following statements is false? So look for one that is different, but hopefully you can know which one's true, which one's false. Limit of this approach is true if f of x exists. Well, if I approach 2 from the left and the right, it looks like it's 2. So that one's a check mark. That one's true. But we want one false, so we know that that one's wrong. Letter B, limit of this approach is 3 if f of x exists. If I approach 3 from the left, if I approach 3 from the right, look at that. It makes that little spike. So that one's true as well. It makes that, it's kind of like a corner or a cusp. Limit of this approach is 4 if f of x exists. If I approach from the left, it looks like it's a little less than 2. If I approach from the right, it looks like it's 4. That one does not exist, so I'll put a little x. Letter D, limit of this approach is 5 exists. Yeah, that one exists. Nice smooth curve. Letter E, the function f is continuous at x equals 3. Yeah, it's continuous at x equals 3. Which one's the one that's different? C, which is the only one that is false. The others are true. Do you guys see how we did it, guys? Yeah, see? And it's okay, guys, if you got it wrong, that's fine. Look, we're just starting. Check it out. This one here is from the 2014 international exam. So take about a minute and see if you can do this one right here, and then we'll chat. And it's okay if you get it wrong, guys. Just make an honest attempt. We're just starting out. All right. Let's see. Roman numeral 1. As x approaches 2 from the left, that equals f of 2. Is that a true statement or no? That's a true statement. F of 2 is negative 1, and limit as x approaches 2 from the left is also negative 1. That's true. Right? Roman numeral 2. Limit as x approaches 6 from the left equals the limit as x approaches 6 from the right. Is that a true statement? Yes. Roman numeral 3. Limit as x approaches 6 equals f of 6. Is that a true statement? No. What two are the true statements? 1 and 2. How do we feel? And look, and I didn't put statistics for that one. Maybe I should have. My bad, guys. Guys, focus. Look, guys, we just started doing calculus, and already we can do free multiple choice questions from the AP exam. Isn't that cool? The simple ones, but still. All right, guys. So here's the deal. All right, guys. I'm gonna save activity 2. That's a handout for tomorrow. Because I know that you guys prefer Delta Math over a handout any day of the week. And I know that because you guys tell me all the time, like, why do we got to do paperwork? Let's do a Delta instead. Like, so for today, we'll do a Delta Math, and tomorrow in lab, when I see you guys, or when I see some of you guys, we'll do an activity 2, the handout for you guys. Is that cool? All right, and make sure that you can log into UH because we will have a UH quiz coming up pretty soon, guys.